Okay, we've got this thing called set builder notation to help us represent some sets of numbers. For example, if we look at this notation here, this is saying that set A is all of the numbers x such that, meaning that, okay, there's going to be some restrictions that follow, not every number x, all numbers x where x is an element of the set of integers, and furthermore, x is in between -2 included and 4 inclusive. So including -2 and 4. So all of the integers from -2 included up to 4 included. Okay? So let's practice this with a couple of examples. Suppose I give you this notation here. What is this saying? Let's read it first. Set A is equal to all numbers x such that x is a natural number and x is in between 2 inclusive and 7 exclusive. 7 is not included because it is not actually equal to 7. So part A says that we should list the elements of set A. So let's do that. We've got all of the natural numbers starting at 2 and going all the way up to, but not including 7, so we'll stop at the natural number 6. Part B, find the number of elements in set A. Well, we can see that there's 1, 2, 3, 4, 5 elements in set A. Is it true or false that the set 2, 4, 7 is a subset of set A? Well, in fact, this is false. And although 2 and 4 are indeed parts of A, 7 is not a part of A. If I drew a Venn diagram of the situation, we can draw set A like this. We've got 2, we've got 3, we've got 4, we've got 5, we've got 6. And if I drew this new set, 2, 4, 7, well, here's 2 and 4, but 7 is not inside set A. And you can see then that this new set, 2, 4, 7, is not a subset of set A because it's not contained entirely within set A, much like we had with the Venn diagrams before, where we had circles entirely inside, and they were subsets. This circle is not entirely inside, and thus is not a subset, so that's false. Alright, next example. Let's first read our set builder notation. Set B is all numbers x such that x is an integer. So x is from the set of integers. X is greater than 3, and at the same time, x must be less than or equal to -1. Well, can you think of any numbers in the world that are greater than 3 and at the same time are less than or equal to -1? Well, no way, there's no such number. The numbers bigger than 3, which are integers, are things like 4, 5, 6, 7, 8, and so on. But none of those numbers are also less than -1. So there are no elements in set B. If we were going to list the elements of the set, we'd have to draw the empty set. So what's the number of elements in set B? 0. There are no elements in set B. And what's another way of notating set B? It's the circle with the line through it that represents the empty set, otherwise known as the null set. Alright, P and this symbol, which looks a lot like a U, Q, is the notation for the union of sets P and Q, and is the set made up of all elements which are in P, or are in Q, or are in both. Meanwhile, if I turn that U shape upside down, so it looks a bit like an N, it is the notation for the intersection of sets P and Q. And that's the set made up of all elements which are in both P and Q at the same time. And so the key word here is or, and the key word here is and. I always remember it where the one that looks like an N is the intersection. It means end. There's this N in all of them. Now, if two sets have no common elements whatsoever, then their intersection is the empty set. Let me draw this for you. Imagine that we've got a set over here, and then we've got another set over here. You'll notice that they are not overlapping because there's nothing which belongs to both of them, like there might have been if they were overlapping. In this situation, that shaded part is the intersection, isn't it? All the numbers that belong to this one and at the same time this one. Here we've got no numbers that belong to both, so the intersection, there is no intersection. The intersection is empty. And we would say in this situation that the sets are disjoint. Another word for disjoint, or another expression meaning two sets that have nothing in common, they are known as mutually exclusive. Imagine that you've got a circle of friends, and then there's this other clique, this other circle of friends, and you guys, you don't include any of them, you exclude all of those guys, and meanwhile they're equally snobby, they exclude all of you. That means that your two circles of friends are mutually exclusive. Both of your circles are excluding all the members of the other set. Alright, let's look at an example. Suppose that we've got set M, which is composed of the elements 2, 3, 5, 7, 8, 9, and set N, which has got the members 3, 4, 6, 9, 10. What are the elements of M union N? That is to say, all the elements that are inside M, or N, or both. Let's list them out. 2, 3. Over here I've got a 4, so that's included. Here I got a 5. It's not actually necessary to write your numbers in order, but it's nice if we do. I've got a 6 over here. I got a 7, 8, 9 over here. In fact, 9 is an element of both sets, but that's okay. I only need to write it down once. And lastly, I've got 10 over in set N. There we go. It turns out, that I've actually got all of the integers from 2 through 10. So if I wanted to write this in set builder notation, just for practice, I could say that I've got all values x, where x is a natural number, and, 2 is less than or equal to x, which is less than or equal to 10. There's a couple of other ways that we could have written set builder notation. We could have said, for example, that x is greater than 1, but not equal to 1, and x is less than 11, but not equal to 11. And that would also be true. We could have also said that x is an integer in between 2 and 10 inclusive. So there are different ways of using set builder notation. Alright, part B. List the elements of M and N, M intersection N. Now we're looking for the numbers that appear in both sets at the same time. Well, 2 doesn't appear in N, but 3 appears in both. 5 doesn't appear in N, 7 doesn't appear in N, 8 doesn't appear in N, but 9 does appear in both, so the only elements that appear in both are 3 and 9. Part C. Are M and N disjoint sets? Well, no, because their intersection is not empty. That is to say that our situation resembles more this one up here. Let me draw kind of a bigger Venn diagram of our situation. Here's set M, which has got the numbers, what did we say? I've forgotten already. 2, 3, 5, 7, 8, 9. So we've got 2, 3, 5, 7, 8, and 9. And then we've also got a set N, which we know is composed of 3, 4, 6, 9, and 10. So the 3 and the 9 are also inside set N, and we've also got numbers 4, 6, and 10 in N, which are not in M. And you can see that our intersection here, 3 and 9, is not empty, and thus, no, the sets are not disjoint. And we can say, since the intersection is not empty. Or if you wanted to say this in mathematical notation, you could say no, because M intersection N is not equal to the empty set. That would be another justification for explaining why M and N are not disjoint sets. Alright, the symbol U is used to represent a universal set. So just imagine that we've decided that we've got a particular set of numbers that we're going to be working with in a problem. That set of numbers is known as U, the universal set. So if set A is a subset of this universal set, which we can notate like that, then the complement of set A, which we denote as A with a little thing beside it, like an apostrophe, that's the set made up of all elements of the universal set, U, that are not in set A. So you can imagine then that if I had a universal set 2, 3, 4, 5, 6, 7, 8, 9, 10, these are all the numbers I'm dealing with in the problem, and let's pretend that set A was 2, 3, 4, that must mean that the complement, which we can read as A naught, would be everything else in the universal set, 5, 6, 7, 8, 9, 10. Now what is the intersection between A and A naught? So what are the elements that we have in common between 2, 3, and 4, A, and 5, 6, 7, 8, 9, 10, A naught? Clearly there are no elements in common, so the intersection would be empty. However, the union of them, meaning all of these numbers in A or all of these numbers in A naught, that would be the entire universal set. And the number of elements in set A naught, well, let's think, that must be the number of elements in all of the universal set minus the number of elements inside set A, and that would leave us with the number of elements that are in set A naught, the complement. So it's the number in set U minus the number in set A. And the last series of examples. Let's suppose that U is all of the integers from -5 up to 5. You'll notice that the -5 is included, but 5 is not included. Meanwhile, A are all the natural numbers from -3 exclusive up to +3 inclusive. And B and C have been given as lists of elements, which is a little bit easier to understand because it's not in set builder notation. It's more explicit. Alright, we need to list the elements of set A. Well, we just described it. That's going to be everything from not including -3, so -2, -1, 0, 1, 2, and 3 is included. What are all the elements that are in set B naught? Well, remember that our universal set includes everything from -5 included up to 5 not included. So which of the elements in the universal set are not in B? Alright, well that's going to be then -5 is not in B, but is in the universal set. What else? -2, -1, 1, 3, and I think the last number that fits inside my universal set but is not a part of B is 4. Okay, so those 6 elements are in B naught. Part C, what are the elements of A union B? So the things that are inside A or B. So one or the other or both. So we've got everything that was inside set A and everything that's inside set B. So we combine those two lists together. And if I write it from smallest to biggest, I'll start with these two, -4 and -3. And then we've got all of our things that were in set A, -2, -1, 0, 1, 2, which 0 and 2 also happen to be in B, but that doesn't matter. I only need to write them down once. And lastly, I've got this last element of set A, 3, and I'll close up my set.